Good morning. My name is Michał Bessler. I'm machine vision engineer in Adaptive Vision Studio. During this presentation, I would like to talk with you about the camera calibration. What it is exactly? When should we perform the calibration? How we should do that? And later, in the second part of my presentation, we will put our hands on the practical example and we will see how to calibrate camera inside Adaptive Vision Studio. Okay, let's get started. So, we can say that camera calibration is creating an image deformation model. But what does it mean exactly? You can see that on the right side, on the top right side, we have got an image with objects not lying not on parallel lines, but rather on some kind of arcs. We can clearly see that the image is somehow deformed. We can say that that's the lens distortion, and during the process of image calibration or camera calibration, we are removing this distortion so that later we can work on an image with objects or lines parallel to each other. We can see the image after the rectification in the bottom right corner. So we can say that calibration is creating a map of the distortion of our lens and camera setup. Another requirement related to the camera calibration is aligning the image coordinate system with world coordinates. The image acquisition is a process of data quantization. So we are saving the continuous object on our scene into a limited number of elements, which are our pixels. During that operation, or either after that operation, we have to evaluate, or we have to find the conversion ratio between the pixels and millimeters, so that we can say that, for example, for 1 millimeter, we have got over 19 pixels. Okay, once we know what is camera calibration, let's see when we should perform that operation. First of all, we have to. It's obligatory in the case that we would like to perform a gauging application. For such application, we would like to return results in real-world units. Results of gauging in pixels will not be meaningful for us. Another group of applications are related to the robot guidance or robot navigation. In such application, we would like to align the image, the points on image, with points in the real world, so that basing on information or basing on localization results on image, we would like to navigate our robot. For example, send the picking position, the rotation angle, and parameters like that. So for at least these two applications, we definitely have to perform a camera calibration. And when we should calibrate camera? Every time we encounter a problem with lens distortion. In fact, probably all the lenses has some kind of distortion. Some of them, sometimes it is less visible, sometimes it's much more visible. And every time we have got some problems during creating our application, we should perform the lens and distortion process. Another requirement is related to the perspective distortion. Let's imagine that our camera is mounted obliquely to the world plane, to the image plane. At that point, we would like to, let's say, theoretically or mathematically transfer the camera so that the image sensor will be parallel to our image plane. In such cases, camera calibration will probably ease our further image processing, and it will be very beneficial for us to operate, to do this process at the beginning of our inspection program. In fact, the camera process of camera calibration is very useful during many applications, and it only depends on your setup and on the requirements of your client whether you should perform that operation or not. For some quality inspection or some kind of counting application, the calibration may not be necessary. However, for many other applications, I highly recommend to perform that operation. Okay, once we know when to do it, now let's see how we can calibrate our camera. So we need a calibration pattern. We need a grid of known features or of known and easily and features easy to recognize on the image. A good example is the circle board or the cheese board. In each cases, we have got a clear either dots or squares, and we can use both of the grids for image calibration. So, what are the guidelines for creating a good calibration grid? First of all, it should be accurate. We cannot expect a good accuracy from the software once we provide an inaccurate calibration grid. Printing a grid on ink printer is not very good choice. First of all, most of the printers has different scale along X and Y axis. Another problem related to the just a sheet of paper is that it's not rigid, and our calibration grid, calibration board should be rigid so that we don't get any additional or in fact artificial, let's say, hills on the image. Then another requirement is the good contrast between the foreground and the background. As on the examples above, we have got a black object on white background. We can also have it in the opposite polarity. However, as a rule of thumb, it's good to have about 100 values of 100 brightness level differences between the background and the foreground. And the last requirement pointed here is that the calibration grid should be large enough. Of course, we don't have to cover the entire work plane with just one calibration grid. We can use a number of images with calibration grid placed on in different position on image, so that finally it will cover our entire work plane. But it definitely should cover the entire work plane, because otherwise on the areas where we don't present a known pattern, we don't present a grid to our system, we cannot expect accurate and reasonable results after the calibration. Okay, so it's clear for us when to do it, or why to do it, when to do it, and how to do it. So now let's see how to perform this operation on, let's say, real example. That's the image of my setup right now. So I will now switch to Adaptive Vision Studio and we'll start the process of camera calibration. Okay, we have got the studio in front of us. In my setup, I have got a Gigi Vision camera, so I will add a Gigi Vision filter. For that, I will insert it to the program editor. I will move it to the right section, to the acquire section. And as there is still a question mark here, so I have to specify the camera address. I will select my camera and I will start the acquisition. Okay, we have got the grid on the picture. So now I will start acquiring the images. I will save the first image. Okay. Move it a little bit to cover the entire scene. Okay, then in order to calculate the focal length of our lens, I have to present the grid at some angle to the camera. So I use a box to mount to put the grid at some angle. I will rotate it. In that case, I have got some reflection, so I will move it a little bit more. Okay, one more picture and one more picture with two boxes, so that we have got the angle is much more significant. Okay, I have got 6 images. That's definitely enough for this case. So now let's stop the program and create the rectification map. I will go to the Computer Vision 2D section and I will find a Remove Distortion tool. I will add a Rectify Image and I will connect the image to this filter. Now I have got still a question mark, so I have to specify the rectification map. Once I click this button, a GUI of the Calibration Editor appears. So here we can perform our calibration process. I'll maybe limit it a little bit so that the preview will not obstruct the visibility. Okay, so as you can see, this process is divided into 3 steps. And during the first step, we'll perform the camera and lens calibration. So I will click this button and I will add previously acquired images. We have got our 6 images. Okay, and first we have to detect the circles. So I will scroll a little bit and I will measure the diameter of my dot. It's about 20 pixels. So I can see that the expected circle radius 10 is fine for this case. So I can press the button for grid localization. And as you can see, we were able to localize the grid correctly. Let's go through different images and see how it works. Okay, for example, here we have got some kind of dirt. So maybe I will increase the threshold so that it will not influence our calibration process. Okay, now it's removed. So it looks okay. Yes, it looks perfectly fine, even on the calibration grid mounted at some angle. Then I have to specify the camera parameters, and we have got 2 lens types available. We have got a pinhole camera and the telecentric. The difference is between because we are using a different distortion distortion types under the hood. For pinhole, we are using perspective projection, and for telecentric, we are using orthogonal projection. Okay, I have got a pinhole camera. I changed the parameter, so I have to localize the grid once again. Okay, then I have got possibility to specify the focal length of my lenses. However, once I use a calibration grid at some angle to the camera, I don't have to do that manually because the algorithm under the hood will create it by itself, will calculate it by itself. Okay, then we have got 3 distortion types. We have got the divisional distortion type. It's the, let's say, the simplest one. It requires, it's the, let's say, the easiest to calculate. However, it's not recommended for very accurate applications. Also, we should use the divisional distortion type in the case that we cannot present the grid across the entire image. Then we have got a polynomial distortion type. This is fine for most of the cases. And finally, we have got a polynomial with thin prism. That's a distortion type dedicated for the telecentric lens. Okay, once again, I play with parameters, so I have to localize it. Finally, when the parameters are set, I can compute the camera calibration model. Okay, once the model is computed, we are switched to the results and statistics tab, and we get information about the raw projection error, the average as well as a maximal, and we got information about the camera parameters and lens distortion coefficients. Okay, let's switch to the presentation for a second. So as we are talking about creating rectification map, and the first step is camera calibration, during that step we are modeling the intrinsic camera and lens parameters. So we are detecting and calculating the focal length of our lens. We are detecting the distortion coefficients as well as the principal point location. In fact, this operation can be performed beforehand so that once we adjust the zoom, the aperture of our camera, we can perform the camera calibration. We can perform this step of camera calibration. It can be even in the office before moving to the production line. However, it's crucial to not change any parameters after this operation is done, because any changes in the zoom, focus, or aperture will void the calibration, and we'll have to perform it once again. Then, removing the lens and putting it back again will also maybe not destroy, but will also influence the calculation, and it will not be exactly the same setup as we prepared before. Even replacing the camera to the practically exactly the same model, it will void such parameters. So it is very important to remember about these requirements. Okay, once the camera is calibrated and we know the distortion of our lens is known, let's move to the word to image transform. During this step, we are computing the extrinsic camera and lens parameters. So we are modeling the position of our setup or of our camera in the world coordinate system. So we can do it in the two ways depending on our application. For gauging application like ours, we'll specify the distance between the centers of the dots. However, for application and for robot guidance applications, we should use a robot arm to precisely navigate to the characteristic points of our calibration grid and provide that word coordinates in our editor. For such cases, I highly recommend you using a calibration grid with some additional, let's say, circles and holes inside. Using that calibration grid, we'll be able to very precisely navigate with the calibration pin. And when this operation should be repeated, every time our distance to working plane change, every time we have got some kind of rotation or replacing the camera, any repositioning will void the acquired or previously computed transformation. Also, swapping the camera will void that operation. So now let's switch to the adaptive vision again and perform the second step of the calibration. So here I can load also a number of images. However, in this case, it has to be images of grid position exactly on our working plane. So it cannot be grid position at some angle to the camera. Okay, I have to specify the calibration grid. The editor get the parameters from the first step. So now I can locate the object, and here I have to specify the circle spacing. It will be 2.5 millimeters in our case. Okay, one more time. Okay, so at that point, we are removing the perspective distortion so that it is very important to have the grid position on our working plane. Okay, here I can also specify the grid thickness. That's very handy if you would like to move our grid a little bit, or if our working plane is below or above our grid, which we are using for calibration. Okay, once we have got the parameters specified, I can compute the word transformation. Okay, and in this situation, we get information about the position in word, as well as the reprojection error, which is visible with these small red arrows. And as I specify the distance, the spacing between grids as 2.5 millimeters, I can see that the second dot has a coordinate 2.5 and 0. Okay, once we perform that operation, we have got the word to image transform computed correctly. We are here also prompt with the information about the reprojection error, which is pretty low for our case. We can move to the last step, which is rectification map generation. Here I will also add one image, and you can see that with this green frame that my image plane is a little bit rotated, as well as I have got some lens distortion because the line is not parallel to the image edge. I can specify the size of this image. However, for this case, we'll use a default parameters. So I will generate the rectification map, and that's our resulting image. Okay, that's how the calibration process looks. Now let's see how our measurements will look. Okay, I will run the program. I will take the calibrated image to the preview, and I will position a washer as an example of our application, and we will see what's the diameter of this object. Okay, I will stop the program. I will add a filter from the fit shape category. I will fit circle to edges. I have to create the image, and I will also add a formula block so that I can calculate I can convert the information in pixels to millimeters. I have to unhide the word scale information, the inverse word scale. I add it to the formula block. I add also a circle here. Okay. So our radius will be, our diameter will be in circle radius times 2 and times in word scale. Okay, I have got the information about diameter. I will run the program. However, I have got still some issues. Something is missing here. I have to specify the mandatory input. I have to specify the fitting field. So I will say that we are looking for the circle in a very broad range. Okay, do I have the circle? Not yet, probably because I have to change the edge transition of our object. Okay, now the circle, the washer, is localized correctly. So I will split the preview and I will show the diameter on the bottom preview. Okay, we have got something like 24.76. Let's try another one. Oh, I have to find a way where I have got these scanning segments. Oh, unfortunately, I will move it a little bit. Okay, 24.7, something like that. And let's see what's the real value. Okay, okay. We talked already about this rectification map generation. And what was the real dimension of our washer? For the big one, we have got 24.76. So that's probably the diameter of this one, right? So it looks that we have got a little bit different. The washers are a little bit different in the diameter. And now let's see how it works for the small washer. We have got 19.625, and let's see the presentation. We have got 19.71. Okay, let's try another example. Okay, here also a little bit different value. And the third one, how it looks. Okay, I have to change the fitting field position. Okay, once again, it's 19.6.652. And let's compare this value with information from our caliper. Okay, I will put it here. And I will change the exposure time so that we can see it a little bit better. Exposure time, let's add 10 here. Okay, so we have got like 1965. And once again, oh. Okay, almost there. Okay, I think that's all for my presentation. I hope you find it interesting. And now let's move to the quality to the questions and answer section. Okay, calibration grid with chessboard or circles have the same precision result. Yes, generally speaking, we have got a very comparable result. In fact, in adaptive vision, we suggest using circles because we have got there is a much better algorithm for detecting the circle center, so it's working much more reliable. How much time does the rectification filter take? What's the camera resolution? Okay, I will switch once again to Adaptive Vision Studio, and we have got the image resolution is 3000 by over 2000, and the process of rectification takes 7 milliseconds for such image. So it's extremely fast operation. In fact, it is because during the calibration process, we are creating something which is called the rectification map. So finally, once the calibration is done, the in each image is only somehow rectified. So we have got information where each pixel should be repositioned. So we are just moving the pixels from the input image to its desired locations. That's why this process is so extremely fast. How to calibrate with robot axis? So generally speaking, for the robot calibration, we have to the first step, the image distortion calculation, is exactly the same. However, on the second step, we have to specify the word units. So here on the second step, we have to specify the word to image transform, and here we'll add a values of our real world coordinates from the robot robot arm. So as I pointed on the presentation, once we have got a circle, for example, with a empty dot inside, we are able to very precisely navigate the calibration pin, and we have to provide that information to this to this Excel to this sheet below. It's enough to provide three values, three coordinates. However, it's good to have at least four. And as I show on the presentation, it's also good to have some additional points so that later we can use it for verification whether our calibration process looks correctly. And finally, once the calibration is done, I will discard the result. There is a group of tools which is called image object to word plane. Using these filters, we are able to transfer objects defined or detected on image to our word plane so that we express it in the robot coordinate system. Okay, I hope that answers your question. Let's go to the another question. Okay, can you explain better the polygonal calibration? with thin prism. In fact, the difference is under, let's say, under the hood. On the the difference is in the math, in the equation used for the distortion coefficient calculation. You will find that information in our documentation. As far as I remember, the exact equations are provided there. However, this, as I mentioned before, this thin prism calibration is designed for the telecentric lenses. Can be calibration done also on 3D camera image? In fact, at that moment, we perform this calibration assuming that we are working just on one image plane. So during our consideration, we are not thinking, or we are not using a depth information. So for 3D image calculation, I suggest you using a ready-to-use 3D sensor, which is pre-calculated for such case. Of course, we have got some tools, for example, for the laser line detection, so that you can try to perform that operation by yourself. However, it will be very hard to achieve the accuracy which is provided by the ready-to-use 3D sensors. So Rectify Image replace over the calibrate word plane filters. In fact, the Rectify Image is the universal, let's say, tool for all the calibration process, for all the calibration steps. In this filter, you are prompted by the graphical user interface, so you can do it easily step by step. The calibrate word plane filters are useful once you would like to perform the calibration using tools, filters directly. So I suggest you please take a look at the example in the Adaptive Vision Studio, which is called the hand-eye calibration. I can switch to that. I don't save the program. Or we have got hand-eye calibration, and here we have got the hand-eye calibration on filters and using the editor. Both of these examples have the same result. However, the difference is that here we are doing everything by ourselves, so we are able to configure each step of the calibration very precisely. For example, if you would like to use a HMI for that operation. So it's extremely helpful when you are preparing an application and on the production line, the recalibration by the operator is necessary. And once I open the editor case, we'll see that all these steps are now performed in just this one filter. And here we are using the image object to word plane for calculation parameters, or for position calculation in the word coordinate system. Okay. Are there some other filters for calibration of image from line scan camera? In fact, we are supporting a area scan camera as well as a line scan camera filters. The line scan mode has been added only recently to our software, and for now we can perform that calibration using the filters. Okay, it's just a case of changing the camera calibration. Give me a second. It's just a case of changing the camera calibration filter. So we switch from the pinhole through telecentric to the line scan, depending on your setup and on your requirements. Okay. Maybe one more last question, because we are already before the time. Okay, what is your recommendation for compensation shaking camera stand? So generally speaking, we have to create our setup so that it will not move, and most of the shakes should be compensated, should be removed mechanically, because otherwise it will be extremely hard to perform a very reliable and precise calibration routine. So maybe it is possible in your case to, for example, stop the machine for the period of calibration and then run it again. However, if the camera and the working plane shakes the shakes are very well visible, then we can think about, for example, averaging information from few frames and basing on that average value, sending or using just this average value. It will always depends on the requirements of your application. However, as let's say a rule, we should try to avoid any movements during the acquisition as well as the calibration process. Okay, I see that there is still quite a lot of questions. I will try to answer them later, because now we have to finish our presentation. I thank you very much for your attendance, and I also encourage you to joining the last presentation about the tricks in Adaptive Vision Studio. Thank you very much.